Okay, testing. Okay, good morning, everybody. Just a quick announcement. I had to make a correction to the assignment. The last question was the instructions were incorrect. It asked you to print out the lines containing some information. You're supposed to calculate the GPA for a given academic year. So the output of the program was correct, but the description of the problem was wrong. So that's just a minor correction there. I have another departmental meeting this afternoon, so I can't hold office hours this afternoon. During reading week, I'll post an announcement on. During reading week, I'll have regular office hours, but they'll be online. The TAs will not have office hours during reading week because they're all students. So they're not supposed to be doing any academic work either. Anything else? Also shortly, so today or tomorrow, there will be an announcement on OnQ explaining exactly what will be on the test after reading week. And there will be sample tests from previous years. Okay, any questions? Super. Scope and lifetime of objects. So we're into the next C notebook. This one is somewhat important. So if you're, it would be good to pay attention to the, at least when we get to talking about the scope of an array. So C has so like Java and Python, there is this notion of scope in C. So the way that scope works in C is pretty similar to how the scope works in Java, right? So if you declare a variable inside of a block, it's only usable inside that block. So that's not too surprising. C also has this notion of lifetime, though, which is not something you've had to deal with in any of your previous courses. So in your previous courses, Python and Java, their runtime environments take care of the lifetime of objects. Right, so in Java, you make an object using new, or in Python, well, you just write something and you get an object. And then you're never worried about when does this object go away. And so in C, that issue should always be in the back of your mind. And so understanding the lifetime of objects in C is important to using the language effectively. C is not object-oriented, but it still uses the term object to refer to stuff in memory. Right, so you have to be careful here because you took 124 and took object-oriented programming. When I say object in 220, it's not the same thing as an object in 124, right? So in C, an object is just something that lives in a chunk of memory somewhere. All right, so the lifetime of an object determines when it's valid to use the object, right? So again, in Java, normally you don't care about this sort of thing. Unfortunately, in C, it's very important. Okay, so let's start with scope first, because scope turns out it's related to the lifetime of an object. So scope in C, there's 4 different types of scope, and we don't care about the last one. So this thing, function scope, you don't need to know about it in this course, and it almost never, sorry, I shouldn't say that. It's unusual to have to deal with function scope in many C programs. But the other 3 show up all the time. So there's something called file scope, there's something called block scope, and there's something called function prototype scope. The third one also rarely, usually doesn't occur, but when it occurs, it's obvious what's happening. So that one's not really an issue either. Okay, so file scope. So you write a C program, you have a C source code file. It turns out you can put a variable wherever you want in that piece of source code file, right? So you can put it inside of a function, in which case it becomes a block, in which case the variable has block scope, right? But if you put it outside of a function, that thing now has file scope, right? So any identifier, so an identifier is just a name, so that includes variables and functions. If an identifier is declared outside of a block or outside of a parameter list of a function, then it has what's called file scope. What that means is that name is usable anywhere at where it was declared to the end of the file, right? So to the end of the translation unit. Oh, the other weird thing is that if you declare a variable or a function outside, a variable or a function at file scope, other translation units can see those, it's possible for other translation units to see those objects, right, or to see those names. So if you declare a variable in one file at file scope, it is potentially usable in another file somewhere else. Okay, so here we have a fairly short program that's got a bunch of variables in it. And it has a bunch of variables, and they all, often the variable names are repeated. Okay, so here we have J, right? So J is not inside of a function, so J has file scope. J here is inside of a function, so it turns out in this case J has block scope. Right? And again, we have another J inside of a loop, which is inside the function f. Right? That J also has block scope, but its scope is limited to the body of the for loop. Right? So we've got three variables named J. There's nothing wrong with this program. It will actually compile to run if you use it. There's J. We have K down here. So K also has file scope. Now in this file, J is usable at this point onwards. So any point after this, J is now usable in your program. Exactly which J is being used depends on which block you're in. J here is usable from this point onwards. So you're not allowed to use K up in the you're not allowed to use this K inside the function f up here because the function f is declared before that K. Right, so K is usable from this point onwards, so it's usable inside the main function here. I don't actually use it, but you could print out its value here if you wanted to. Okay, so the example above illustrates that where a variable is declared affects its scope, right? K has file scope, but it's not usable inside the function because K is not in scope relative to the function f. Right, so if I compile this, run this program as it stands, it should work. So it prints out a bunch of stuff. As soon as you try to use K inside, as soon as you try to use K inside the function f, you now get a compiler error. Right. So K is undeclared. So it's trying to tell you I don't know what K means inside this function. Oh, sorry. Okay, so that's a little bit different than how class variables work in Java, right? So in a Java class, if you declare a variable somewhere inside the class outside of a method, that variable is usable throughout the entire class, regardless of where you declared it. But in in C, that's not the way it works, right? K becomes visible here. Okay, we're going to come back to that example later on in the notebook. Block scope is when you declare a variable inside of a pair of braces somewhere, right? So just like it works in Java. If you have a parameter in a function, so I, this thing here also has block scope, right? So the scope of I is the body of the function f. Right? Again, just like it works in Java. Okay, so let's run this program here and see what we get. Okay, so inside the main method, so remember all your programs start running here, right? The main method immediately prints the value of J, right? So J is that variable up there. Right? So in this case, it prints out 0, and that is the way it's supposed to behave. So even though J is uninitialized up here, it turns out that for block scope variables, they do get 0 initialized, I think. Pretty sure they do. Okay, so we call the function f up here. So we looked f. And now, remember we have this variable J, right? So inside the function, we have another J. So this J variable has block scope, sorry. So it becomes usable on this line. And inside the function, it's also usable. Inside the function, this J takes precedence over this J. Right? So if you were to print out the value of J, which I do right here, right, you're going to get 1 and not the 0 that we got before. Right? So inside the function inside the function, J gets the value 1, which is correct. Or that's the way it's supposed to behave in C. That I there is this I here. So if we add 1 to I becomes 101. And so we get that right there. Okay, now we have a loop, which also redeclares the variable I. Right? So this variable I is local to the loop body. So in other words, here, these two lines here, whenever you see I, it's referring to that I there. The loop also redeclares J. So this J now takes precedence over this J and the other J and the file scope J. So inside the loop body, whenever you print out J, it's always 2. When you print out I, it's 0 and then 1. So there we get I is 0, J is 2, I is 1, J is 2. After the loop, right, that J and that I are now out of scope. Right, so they go away. And whenever you refer to I and J, you're now referring to that I and that J. So when you print out I and J here, you get back 101 and 1. Right, they don't change. And finally, when we get back to the main function and print out J again, right, as far as the main function is concerned, the J that's in scope is this J. We never touched it, so it gets the value 0 down here. Right, so that's the difference between file and block scope. Right, function prototype scope only shows up when you in your parameter list, and it only shows up when you are using arrays. Okay, so here is this is what's called a function prototype. Right. So a prototype is just the declaration of a function. You can also have it's just a declaration of a function, sorry. Right. It doesn't tell you what the implementation of the function is. Right. So there's no body here. And so the way things work in C is that you have to declare a name before you use it. Right. So you have to declare a variable before you use it. It turns out you also have to declare a variable function before you use it as well. Right. Or you have to declare the function and then define it at the same time. So this is what's called a function prototype. It simply says some function that takes in an int exists. Right? And that's all it says. It doesn't say what the body of the function is. Okay, so usually function prototype scope's not super interesting, right? But it does affect the order of the parameters that show up in your parameter list. And so here's an example of when it affects the order of your parameters. Right? So here, our variables n and a have function prototype scope. Right? They're part of the parameter list for a function prototype. Right? The n has to appear before the a n in this case. Right? So that array parameter says that the array a is supposed to have size n in this case. Right? But before you can use n, you have to declare it first. So that n has to show up here before you write a n. Right? If you flip the order of these two like that, so this does it do anything? It doesn't do anything. Sorry, this needs to be defined inside of inside of a main, inside of a full program. This one here won't work. Let me just see what happens when you run. Oh, here it is. So you do get the right error. And so it says here, n is undeclared here. So it's complaining it doesn't know what n is because you declared n after you used it. Right? So there it matters which order you write the parameters in. But that's all you need to know about function prototype scope. Right. Once you run into the error, it's obvious what happens. What has caused the error. Okay, so we know about file scope, we know about block scope. We don't really care about function prototype scope so much. Now we need to talk about lifetime. So the lifetime of an object can be affected by its scope. So in C, there's 4 kinds of lifetimes. We only care about the first 3. The fourth one is a topic for your, operating systems course. So we're not going to talk about thread lifetime of a variable in a thread. But automatic, static, and allocated, turns out those are important for our purposes. Okay, automatic storage duration. That's the default storage duration of an object declared with block scope, right? Or an object that is a function parameter. Right? So if you have a block scope variable, or if you have a function parameter, and you are not allocating memory for that thing, it has what's called automatic storage duration. So what does automatic storage duration mean? It means memory for the object is allocated when the block at which the object was declared is entered. Okay, so the block starts, any local variables you have in that block, memory for them is valid when you enter the block, right? And memory goes away when the block is exited. what am I doing here? There's 2 copies of the same cell, so they're unnecessary. I just want to go read the. Okay. And so there's our parameter I. It has automatic storage duration. Okay. Once you enter the block, the variable I, memory for the variable I exists. Once you exit the block, memory for the variable I is no longer valid. Right. The same is true with J. Right. So once we enter the block that J is declared in, right, memory for the variable J is so there is memory allocated for the variable J. Right. When we exit the block in which it's declared in, there is no memory, or the memory is not accessible, not legally accessible for the variable J. Right. Similarly here, right? So there's our variable I, right? Inside the loop body, I exists. Outside the loop body, that I no longer exists. And the same is true for J. Inside the loop body, J exists. Outside the loop body, J does not exist. So objects with automatic storage duration are not automatically initialized. So if you declare a variable inside of a block, and you don't give it an explicit initial value, then the value of the variable is indeterminate. It could be any value, right? And this often leads to hard to find bugs. So here's a program that computes the sum of the first n integer values, right? So it's going to compute the sum of 0 plus 1 plus 2 plus 3 plus 4 up to plus n, right? So obviously you're going to use a little loop, right? And you're going to accumulate the sum in a variable here. I guess this is the first time I'm using unsigned to store a value, right? If we're computing the sum of the first n natural numbers, that value is a positive value. So here I've decided to use unsigned long to store the sum, right? Why long instead of int? Because n could be very large, right? In which case, if you accumulate the sum in an unsigned int, you can overflow the range of unsigned int. So here I'm going to accumulate it into a long and hope that long is much bigger than int on my computer, and try to avoid the overflow. Anything else here? Right. So we're going to accumulate the sum of the using a loop, and then return the sum. Okay. So if you are, let's see what happens when we run this thing. So here I've got another loop. I'm just going to compute the sum of the first. So the sum of the first 1 numbers, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers, natural numbers. Okay, what do we get? All right, we get the wrong values. That's good. Right? So apparently the sum of 1, so 0 plus 1 is 9 something, which is not right. Right? The sum of 0 plus 1 plus 2 is also some incorrect value, and so on and so on and so forth. Right? What's happened here? Right? You've declared a variable here called sum, and you didn't give it an initial value. Right? So C simply uses whatever value happens to be sitting in memory at this point. You have no idea what value is sitting in memory at that point. You have to initialize the variable here, and now you get the correct sums. Right. So watch out if you're using a variable with having automatic storage duration; it's not initialized. The same is true in Java. So if you declare a little local variable in Java and you don't initialize it, it doesn't have a value yet. Now the Java compiler will warn you about this though, right? So if you try to use the variable later on and it might not have been initialized when you try to use it, you'll get a compiler error. In C, you don't get that error, right? You don't even get a warning. The program compiles, it'll run, and you'll just get some answer. Okay, so that's automatic storage duration. There's also something called static storage duration. This one's a little awkward to talk about because it also, C uses the keyword static, but it means something completely different than the static keyword in Java. Okay, so static storage duration is the storage duration of an object having file scope. Right? So if you declare a file scope variable, it has static storage duration. Right? You can also declare a local variable and mark it as being static, and it now has static storage duration. Okay, so remember the keyword static in Java is different than the keyword static in C. In C, when you mark something as being static, you're saying it has static storage duration, and the lifetime of that object is the entire execution lifetime of the program. right? So at the point when the program starts, anything with static storage duration exists, right? And it exists until the program ends, right? So until your main function returns a value. Right? Okay, so the language guarantees that the value of the object is initialized exactly once before the program starts running, right? So static variables with static storage duration do get initialized, and the language promises they're only initialized once. Okay, so what values do they get initialized with? So if it's an arithmetic type, so if it's a number, it gets set to 0. If it's a structure, every member gets recursively set. We haven't talked about pointers yet, but if your variable has a pointer type, it gets initialized to null, indicating it points at no object. So basically, everything gets 0 initialized. So that's why when you print out J in this program, that J starts out as being 0, and it's guaranteed to be 0. Right? So that J there has file scope. So it has static storage duration. Therefore, its lifetime is the entire lifetime of the program. It gets initialized to 0 before your program starts running. Right? Or I guess at the point at which your program starts running. All right, so you can kind of imagine what a file scope variable might be used for, but it's a little unusual to imagine why you would make a local variable and declare it as being static. And so you can make a block scope variable, declare it as static, right? All the rules for static variables apply. It exists for the entire program. It gets initialized before your program starts running, right? Static variable. And it also has what's called internal linkage, right? So static variables have what are called internal linkage, right? Internal linkage simply means the variable is visible only inside of the translation unit itself, right? So it's only visible inside the file that you declared it in. So that's what happens when you mark a variable as being static, right? So if I was to go up here and mark I as being static, right? It has file scope. It's only visible inside of the file scope.c, right? The way this is declared right now, it's not marked static. So it still has file scope. It still has static storage duration. However, it is visible outside of this file. So if you have another file, I don't know, temp.c, right? Temp.c is able to see that variable j. So it is able to see and affect that variable j. Right? You have to tell it that it exists, but if you tell it that it exists, then it's able to affect this variable. It is able to affect this variable. Okay, so inside of a where am I using? Oh, here. Okay, so we're back to here. Okay, so there's an example of declaring a file scope variable being marked static, right? So here I've got the sum declared at file scope, right? It gets initialized to 0. Now remember, it only gets initialized to 0 once, right? So the first time you use sum, it's 0. Every other time you use sum, it's whatever the previous value of sum was. So this program here uses sum in sum of to accumulate the sum. Right. Here I'm going to print the sum. So I got a little function that just prints the value of the sum. And I run it once. Right. So I compute the sum of the first 10 numbers and run it once, and everybody's happy, right? If you compute the sum of the first 10 numbers, it is in fact 55. Right. The error here is that yes, you're initializing the sum to 0, but it only gets initialized once. So if you call sum of a second time, you're not going to get the correct sum. Right? You're going to get the sum, including the sum, including whatever value. Oh, sorry, including whatever value this was set to by the previous call to sum of. So here I call it twice. There's sum of 10, and I call it a second time, and you don't get 55 twice. You get 55 and 110. Right? So the error here is that sum of does not set sum to 0 before accumulating the sum, right? Which is easily fixed. Right? So you could easily fix this problem by writing sum equals 0 here. Right? And away you go. Right? The real issue here is that you shouldn't be using a static variable at file scope to be storing the sum, right? It's probably better to make a local variable here and accumulate the sum using the local variable. Now, it turns out we don't use static variables much in this course, but you can, but a function can declare a static, a variable as being static, in which case the variable, static functions. So there are also static functions in C. So you can declare a function as being static, right, which doesn't do anything except make the function only visible inside the translation unit itself. Right, so it's like you declared a private method inside of Java, right? Private method's only visible inside the class. A static function is only visible inside the translation unit. Okay, so what happens if you make a block scope variable that's static? So a block scope variable that's static can occasionally be useful. So it behaves the same as a static file scope variable, right? So it exists when the program starts running until the program's finished running, right? It gets initialized exactly once. So that's the other thing you have to remember, right? It only gets initialized once, but because it exists for the entire length of the program, you can use that little local variable to remember stuff between function calls. Right, so here's a function called count. This thing basically behaves like a counter. And so it's going to remember what was the previous count when you called the method last. Right, so the function count here lets you change the value of the count by some non-negative value. Right, so count 1 will increase the count by 1, count 2 will increase the count by 2. Right, internally, the count is stored in a static block scope variable. So this value gets initialized to 0 once, right? Every time you call the function, it increments that value. Potential overflow. If increment is greater than 0, the increment's always greater than 0. Potential overflow bug. Sure. All right. Oh, I guess the increment can technically be 0. So if the increment's greater than 0, we're going to add the increment to the value. I wonder why it's written this way. Do I? Oh, no, I don't have a note here. Okay, I suspect that used to be just int. But anyway, it's fine. We're just going to add the increment to the value each time. Right? Technically, this can overflow if you increment the counter enough times, or if you increment it with a large enough value, it will overflow. But that's just the way that ints work in C and Java. Right? So here, the count function returns back the value of the value of the variable value. So when we write count 0, we're going to get back 0, right? Because the initial value is 0, and then we add 0 to the count. Right? So the current count is 0, which we got by calling count, passing in 0. Right? When you write C equals count 1, C now has the value 1. Right? When you add 1 more to the count, right, it's going to be 2. Right? When you add 1 more to the count's going to be 3. Right? To get the value, to get the current count, you just pass in 0. Right? And that'll give 3 in this case. Right? So here you can use a static block scope variable to remember stuff between function calls. It's occasionally useful. It's not super useful. So functions that retain information between calls are somewhat uncommon. They're hard to use correctly. There's only one example that I know of in the entire C standard library that actually uses this technique. And so that's there's a string function called strtok that actually uses a static local variable to keep track of information between function calls. Right. All right, allocated storage duration. So an allocated storage duration, this is going to be new for us. So you haven't seen this yet in 124 of Python. So an object having allocated storage duration is one where the programmer is saying they want to control the lifetime of the object. So to control the lifetime of an object, the programmer is responsible for creating the object. They're then responsible for using the object, and then they have to get rid of the object, because if they don't get rid of the object, you've got an object that exists that's no longer needed. So it's eating up memory and possibly other resources that the program might want to have back. Right. So the process to create an allocated storage object is to request memory for the object, use the object, and then release memory that was used by the object when you no longer need the object. Okay, so why might we want allocated memory objects with allocated storage duration, right? So imagine you have a function, it needs to return a value, right? So inside the function, you make a little local variable. Let's imagine that it makes an array inside the function, right? So if you make an array inside of a function, we know that the array doesn't exist after the function returns, right? And so there's no way for you to return the array back to the caller, right? So you can imagine that it's probably pretty useful to be able to return an array from a function. So what do you have to do? You have to create an array having allocated storage duration and then return something related to the array. So if you need something that persists across calls, across multiple function calls, that something probably needs allocated storage duration. Right. Okay, so the clearest example of when you need to do this is when a function wants to create and return an array. Right. So here is a okay. All right, so there's a few things we need to talk about here in this function. So here's an array called int array, right? It takes in an argument of named length. The type size t we haven't seen yet. So this is the first time we've seen size t. So size t is not itself an actual type, right? It's the name of a type that represents a value that can store the largest possible object in C, right? So in other words, it's unsigned, and it can hold, it's guaranteed to be able to hold a value that represents the largest thing that you can allocate in C. Right? Its actual type depends on what your depends on your compiler and your operating system. So I think on my computer it's unsigned long, but I can't remember what it is exactly. Okay, so when you're working with things like the size of an array or the size of an object, it's common to see the type size t used to refer to that those values. Right. So this is going to make an array of that length. So odd thing number one in C is that zero length arrays don't exist or are not supposed to be allowed. So the language says if you try to make an array of size 0, the result is undefined. Some compilers allow it, some compilers don't. So here, if someone asks for an array of size 0, I'm going to make it 1. So that's technically the smallest array that you can have in C. Right? The empty array does not exist in C. Not supposed to exist. Okay, so this is the only way that we know how to make an array. So I'm going to make an array like that. Right? What's the problem? Right? The problem is this is a variable inside of a block, so it has block scope. Right? So the array lifetime starts here. Right? The array lifetime ends after this line. So you're returning back something that looks like an array back to the caller, and when the caller gets the return value, that array no longer exists. So if they try to access the array down here, it's undetermined. So the language says it's undefined what will happen at this point. Okay, notice here the return type is funny, right? So this is that return type there is what's called a pointer to an int. We haven't seen pointer types yet. We're going to see them in the next lecture after reading week, right? Turns out you're not allowed to return an array from a function. It's not allowed. The best that you can do is return what's called a pointer to the first element of the array. So in other words, you're allowed to return the memory address of the first element of the array back to the caller, right? When the caller gets back a memory address, which they also store in a pointer, so int space star a says that a is a pointer to an int, right? You can then use a like it was an array. So you can use the square brackets and access the elements out of the array that way. We'll talk more about pointers in the next lecture. Okay, so what happens here when you run this program? So the problem is it gives you a warning, right? But the program does compile. and it does in fact run. Right? If you look at the warning even tells you array lifetime, function returns the address of a local variable. So the compiler is trying to warn you, you're returning something that doesn't, you're returning something to the caller. The object that the caller gets back doesn't exist when the caller gets back, gets the return value. However, it does run. And so that line there indicates that the program did in fact run, but it crashed when it ran, right? So here executable exited with code -11. Doesn't tell us anything useful, but the program did run, right? And so what happened here is that when you tried to access the first array element here, you're accessing an array element, you're accessing an element out of an array that doesn't exist, right? The lifetime of the array ended right there. And so this program dies, right? It dies when you, it crashes when you run the program. And so it looks like there's no way to actually return an array effectively from a function, right? But there is. The answer is that you have to not return an array with allocated storage. Sorry, not return an array having block scope lifetime. You need to return an array having allocated lifetime. Okay, so how are we going to do that? Well, we're going to do that in a later notebook. So when we talk about allocating and freeing memory, that's when we'll see how you actually return an array from a function. So that's in this notebook right there, which I don't think is the next notebook. Okay, so that finishes this particular notebook, right? So remember, you have two important types of scope, right? So file scope is when you declare something outside of a function, right? Block scope is when you declare something inside of a pair of braces. And then you have storage duration, right? Or lifetime, right? So automatic storage duration, that's the lifetime of a object declared inside of a pair of braces, right? It exists when you declare it, and then it goes away after you use the block. Static storage duration or static lifetime means that the object lives for the entire length of the program, right? And allocated storage duration lives for as long as the programmer lets it live. Okay. I wish this bar would go away. Oh. What is the next notebook, and is it worth looking at declarations? Sure, let's start this notebook. Okay, so in C, just like in Java, you have to declare variables, and in C, you have to declare functions before you can use them. So a declaration in C is simply something that introduces one or more identifiers. An identifier is just a name into the program, and it specifies their meaning and properties. So what it means by this is it means if you have a variable, you have to say what its type is, right? If you have a function, you have to say what its return type is, what its name is, and what its parameters are. Right? The declaration does not necessarily define a function. Okay, so variables, you know how to declare variables, right? Because you can, you all know Java. And so here, int x double y does exactly the same in C, right? You can also do this in Java, although I never show you this in 124, right? You can declare multiple variables of the same type on the same line, right? So int a, b, c says that a, b, and c are all ints and they exist. But if the variables have allocated if the variables have if the variables have automatic storage duration, they are not automatically initialized, right? So here, x, y, a, b, and c could have any values. What do they have, right? And in fact, in this case, they do in fact have any. They have arbitrary values. We know about initialization, right? So you know that you can initialize the variable when you declare it, right? So when you run this program, it behaves in a more predictable way, right? We've initialized the variables, so they all have predefined values. You can mark something as being const, so we saw this in a previous notebook as well, right? Const simply means that the variable is read-only. You can only initialize it. You can't redefine it, right? You can't reassign back to it. So here, whoa, sorry, right? That declares a const variable called x, right? x is initialized to the value 1. This declares a constant variable y. Y is not initialized to anything, so it could have any value. The next line is an error, right? You cannot assign to a const variable, right? And that one gives you an error, right? And it tells you assignment of read-only variable. Okay, so in C, the const becomes part of the type of the variable, which is a little bit odd, right? So in Java, you can have a modifier, and it doesn't become part of the type, right? In C, that const becomes part of the type. So the type of int here is const int, right? And the type of y here is const int. Right? It's not plain old int. If it was plain old int, you could reassign to it. Functions behave similarly to methods in Java, except there's no access modifiers. Okay. So a function simply states a function declaration or a function prototype simply states the return value, the name of the function, and the parameters of the function. The name x and y here is not required. Right? So these the names here actually are unimportant as far as the prototype is concerned. Right? You only need to know that that's a double and that's a double. Okay, so here, all right, is our function prototype or our declaration of max2. Right? So this simply says there's a function called max2, it returns a double, takes in 2 doubles as its arguments. There is a function declaration, but it's also a definition. Right? So this gives both the declaration and the definition of max3. Right? Max3 returns a double, takes in 3 double values. Right? And it simply calls max2 twice. Right? It computes the max of x and y, and then it computes the max of that and z. Right? So it uses max2 to compute the max of 3 values. And then there's a little main function that calls max3. Right? So on its own, sorry. Okay, so this program on its own, right, or this file on its own does not constitute a complete program. Right, so I'm just going to switch into my, sorry, not this one. I have to start a new console. Hang on. Okay. Where am I? Let's see. This is. Okay, so max2, so cat next. Whoops, sorry. Oh, sorry. Cat uses max2. There we go. So there's our program right there. So it starts with an include statement because I want to print something out. It declares but does not define max2. It defines max3 and then uses max3. So this is not a complete program. It's not a complete program because the definition of max2 is missing. Right? You can compile the program though. So you can compile this file. So GCC, sorry, I just want to see what's in here. Okay, so GCC uses max2. So you can try to compile the program. When you compile it, you get a funny error. So you get this thing user bin LD, right? So LD is the linker on my computer, right? If you're on Mac, it's probably a different program. But if you're in Linux, it's probably LD, right? And it complains that in the function max3, you're using max2, right? And the compiler does not know what max2, what its definition is. Sorry, the linker doesn't know what the definition of max2 is, right? So remember a couple of lectures ago when we learned about the compilation process, or maybe it was the previous lecture, your program gets pre-processed, then it gets compiled, then assembled, and then the linker runs, right? And so in this case, it's the linker that's failing. And so it turns out you can, in fact, compile this program. So GCC, so -C means compile and then stop, right? So don't do the linking stage. Right, and that succeeds. Right, and that produces a file that ends in .o. right? And so there's your object code. Sorry, this does the assembly as well. So there's your object code produced from compiling uses max2.c, right? But that's not a complete program because we still need to say what is max2, right? And so there's another file called max2.c. Right? And inside max2.c, there's nothing but the definition of the function max2. Right? And so you can also compile that. Right? And now there's max2.0. So there's your compiled version of max2. There's your compiled version of uses max2, right? And now we can stitch these two things together to complete the program. Right? So GCC minus O uses max2. So that's going to be the name of my complete program, right? And I can tell the compiler to stitch together max2.0 and uses max2.0 like that. Right? And now I've got a complete program uses max2. Right? And that computes the max of 5.2 minus 1.3 and 4.9 and tells you it's 5.2. Right? So there's an example of a program that's defined in two translation units. Right? It's defined at max2.c defines the max2 function, uses max2, defines the rest of the program that calls max2. Right? Two different translation units stitched together to produce a complete program. Okay, so the question is how does uses max2 know that max2 exists, right? So inside uses max2, right, we actually put down the declaration of the max2 function, right? Inside of our file, max2.c, right, we have a function that matches the declaration up here. Right? So in this case, when the linker runs, so the compiler's happy, it knows what max2 looks like. The linker's happy, it can find another function, it can find the function max2 in a different translation unit, and everything gets stitched together and everybody's happy. Right? The problem is this line here in it uses max2, right? We had to put this line in specifically ourselves, which is going to get really annoying if you try to include, if you have a bunch of functions declared somewhere else. Right? Now you have to go and find all of their declarations, copy them into your file, and that you can imagine is going to be very error prone. Right? If you change the definition of the function in one of your translation units, right now you have to change its declaration everywhere you've used it. So you don't want to do that, right? So the solution to this problem are these things called header files, right? And so I told you this was what I talked about, I guess, on our first C lecture, right? There are these things called header files, right? We've been using them, so standard io.h, right? And I told you earlier on that all these things is that they contain the declaration of functions, right? They don't contain their definitions. And this is exactly why you want to use a header file, right? I don't want to have to type in the declaration of max2 every time I want to use it, right? So the idea is you put the declaration into a header file and you simply include the header file every time. Oh, sorry, this one's telling you what not to do, right? So the new C program will say, well, look, I declared max2 and max2.c, and I know about this include mechanism, right? I can just drop the contents of the file into my program using include, right? So there's a big comment here, don't do this, right? The problem is that if you actually compile this program, it does work, even though it says don't do this. Right, so there, include, right, so bad uses max2, right? Compiles just fine, and it runs just fine too, right? And so the new C program will say, well, why don't I just do it this way every time and include my source code file each time, right? So at first glance, this works, right? Compiling the program works, running it works, right? Now, the first clue that something is wrong is when you try to compile the program like that. right? So if you just compile the program bad uses max2.c, everything works fine, right? If you say, well, look, I've got this file max2 where max2 is defined in, I have to compile that as well, right? Right? Now you get a problem. Now a problem occurs. So now LD complains. So now the linker complains, right? It says in the function max2, there are multiple definitions of max2. Right? So what the heck has happened here? Right? So when you include the header, when you include the source code file, right, you get the definition of max2 inserted into bad uses max2. Right? So max2 is defined. Right? When you try to compile your program like this, right, it compiles max2.c, so it sees the definition of max2. It then compiles bad uses max2.c and sees the second redefinition of max2. In C, you're not allowed to have a function that has the same name twice, more than once, right? So here, it's trying to put together a program that contains two definitions of max2, even though they're defined the exact same way, right? And so now the linker complains, right? If you try to compile everything separately and stitch together yourself, the linker will complain again, right? So never include a source code file like that, right? So don't do that. Never include a C file inside of another C file. Instead, make yourself a header file, put the declaration of the function in the header file, right? Inside your program, include the header file that you want to use, right? I guess I have to stop there because we're past time, we're over time. So after reading week, I'll come back and explain what that means. Right. All right, everybody, have a good reading week. Oops. Second here.